Hi everyone, I'm Aditya from University of Michigan, and I'm presenting our UAI paper, No Regret Exploration in Contextual Reinforcement Learning. This is joint work with my advisor, Ambuj Tewari. The motivating case for our setting is reinforcement learning for a heterogeneous population. Reinforcement learning can be used to model a lot of decision-making problems. For instance, consider the healthcare environment, where the patient is the environment and the agent has to take treatment actions after seeing certain health related states for the patient, and the goal is to maximize the total reward, where reward is a survival related signal. Now many domains involve interaction with different entities, for example interacting with different patients in this scenario, and we don't only need to share data across all these different entities, but we also wish to learn personalized policies. Similar issues would arise when you consider recommender systems, tutoring platforms, or virtual assistants, for example. Now, we model this by using this relatively recent framework of contextual MDPs. To understand it, let's look at a typical episodic MDP, where the agent interacts with the environment for a fixed number of steps and takes actions after observing states and observes the reward after it. The true model would consist of next state distributions, reward functions, and initial state distributions. Now, the goal of the agent in a single MDP is to simply learn a policy pi, which maximizes the expected value. In contrast, in a contextual MDP, the agent interacts with multiple environments in a sequential fashion. Precisely, at the beginning of each episode, the agent observes a context xk, which belongs in R to the D, and now the agent chooses a policy pi k, which depends on the context. And then it receives a total reward for the th steps from the MDP mk, which can now vary with these contexts. Now, the goal here is to learn a context-dependent policy so as to optimize the expected value over any sequence of contexts that you can get. So we are looking into an adversarial scenario where the context can vary arbitrarily. Now, the performance criteria which we consider is regret over k episodes, where the instantaneous regret is simply the value gap for the agent. It's easy to see that one cannot expect to learn a good policy if the MDP varies arbitrarily with the context. And previous works have made varying assumptions about this mapping from context to MDPs. And a key focus here for us would be linearly parameterized MDPs, which again comes with certain caveats where we need to put simplex constraints over the context space. So can we improve over the linear structure and also remove the required constraints? We use generalized linear models, which effectively gives us linearity, but also allows us to model next state distributions pretty well. Precisely, the MDP dynamics and reward functions in our case would be parameterized using GLMs, where the next state distribution for a given state action pair is written down as the gradient of a certain link function over the projected context to an s-dimensional space, and the reward function also is a linear function of the context. It's easy to see that we are taking inspiration from the canonical GLM family case, where the expectation of a random variable is defined by the gradient of the link function. We will assume that this link function phi is strongly convex and smooth function for designing estimation algorithms. And for example, the multinomial logit mapping case, where the next state probability scales exponentially with the score function, and the linear parameterized MDP case are special instances of the GLM setting. We propose online exploration algorithms by building confidence sets. As such, we will need to build an online estimation method for these parameters W, SA, and theta SA. We propose and analyze an online Newton step-based method, which works as follows. We first give an online learning formulation of the problem, where the agent observes the context xt and one sample from the corresponding categorical distribution. Using this, it updates the parameters wt by taking an online Newton step update and uses a strongly convex and proper loss LT derived from the link function. Note that here it only stores the covariance matrix of context and therefore is also memory efficient. The confidence interval guarantee that we can give is a high probability anytime guarantee, whereby the true parameter W star lies in an elliptic ball whose radius scales polynomially with the number of states and dimension of the context and depends logarithmically on the time index. We first propose an optimistic exploration algorithm for GLM CMDPs, which we call GLM ORL, where at the beginning of each episode, the agent observes the context and estimates the MDP and the confidence sets for all next state distributions and rewards. Then it computes an optimistic policies by using a reward bonus which depends on the confidence set for the MDP in value iteration. And then using the optimistic policy, it unrolls an episode. After observing new samples, it refines the parameter estimates using ONS. So the regret guarantee we can give for this algorithm is a high probability anytime regret bound, whereby we get a polynomial regret dependence where we scale as a square root of k in terms of number of episodes and have optimal dependence on actions. And we are suboptimal in D, S, and H, but it's typical for algorithms derived from UCRL2. It's also important to note that we improve over the previous linear MDP regret bounds by a factor of square root S. We also propose an exploration algorithm using randomized value functions, where the agent again estimates the MDP for an episode and the confidence sets. But instead of using a fixed optimistic bonus, it uses randomized value bonuses in value iteration. And after the end of the episode, it again refines the parameter estimates using ONS. For this algorithm, we can also give a high probability anytime regret bound, where the dependence on A and K remains the same, but we get worse dependence on number of states and horizon. The dependence on D is again the same. In addition to this, we also give a pack-style mistake bound for the optimistic reinforcement learning algorithm. We give a lower bound construction for GLM CMDPs using logit links and the linear function. And we give a generic conversion from a no-regret parameter estimation algorithm to a no-regret CMDP exploration algorithm. To conclude, in this work, we propose optimistic and randomized exploration methods for CMDPs using this new framework of GLMs. Our GLM CMDP framework subsumes previous linear CMDP frameworks. We also show an improvement on previous bounds by a factor of square root S. For future work, we would like to investigate how these contextual models help when using function approximation and derive minimax regret guarantees for the GLM case. And it would be nice to investigate these algorithms empirically on a practically relevant benchmark. For any questions, please visit our poster or please feel free to email me on this address. Thank you.